All right, so we're actually going to kind of go through the parts of this. I have a little bit of lesson kind of brought up. Sometimes I kind of go through notebook. I try to plan this out a little bit better so we can kind of like go navigate, because honestly, I was starting to get confused about like what notebooks I wanted to pull up. But I'll make sure to save this and send this out, you know, through the repo that you guys can kind of follow along and stuff like that, and kind of like review like parts of it as we go through. Okay, so I'm going to kind of do this more. I was going to have you guys break up into groups, but just to make sure we have enough time, I'm just going to have you guys kind of like ponder this for a second, and then maybe have some volunteers to answer. So just kind of based on what we learned so far, what you already know about statistics, whether that's from the curriculum, from your own knowledge, just basic idea, you know, we're just going to answer these questions. And, you know, even if you don't know, that's perfectly fine. Just take your best guess. So I'm going to ask you guys, what's so great about these Gaussian curves, normal distributions, bell curves? Why do I think they're so cool? Why do statisticians think we're so cool, or they're so cool? I want to kind of think for a second, ponder through like what was the whole point of Gaussians, and then if someone wants to volunteer, I think I say Akiva on mute. He's ready to go.
So you can use them uniformly across all distributions.
Yeah. So can you kind of explain a little bit more, like when you say use them uniformly across all distributions?
Regardless of how the distribution is distributed, you can compare all of the distributions using the Gaussian distribution. It's like a converter.
All right, I think I'm going to put some caveats to that, because I think that could be confused a little bit. There's one thing we're going to learn is that we can actually take any distribution of any population and essentially force normal distributions onto it, which is pretty cool. There's another part of it, and I think you kind of said it, Akiva, but I'm going to see if Alvaro kind of expands on it.
I was just going to say that normal distributions, core normal distributions in a sense, because they occur in nature quite often. So it's just a good way of modeling things that occur in nature.
Yeah, that's a good point. Is that normal distributions are everywhere, like their nature and stuff. And I will say we can even create really weird situations that would be maybe not very nature-like, and they still end up being normal distributions. It is a very common distribution. It has some great properties. There's a big thing about normal distributions, which is like, thank goodness normal distributions come out so easily. There's a whole bunch of reasons why this happens, but the really great thing about it is that we only need 2 parameters to ever describe a normal distribution. What are those 2 parameters? Want to take a guess?
Mu and sigma.
Mu and sigma, yeah. So mu, if you guys remember, it's the weird U-looking thing, and sigma almost looks like an O. My wife was actually looking at my code, and she saw like the sigma in there. She's like, what's that weird A thing going on there? And I was like, oh no, that's the Greek letter. And she's like, oh good, I thought my eyesight was going bad. So yeah, basically if you know mu and sigma, you know exactly what that normal distribution looks like. Remember that scary looking equation. Basically that's really useful because we now know the mathematics, we know how to describe that thing. We can do a whole bunch of really cool things with it. Okay, so let's hear. So this is a little more thing that maybe we haven't really talked about, but like, what's the point of knowing different statistical distributions? So not just normal curves, but we mentioned about binomial distributions. We're going to talk a little bit, very briefly, about exponential distributions, Poisson distributions. What's the point of knowing all these different distributions? Like, what is the benefit?
Different types of data will form different types of distributions. So you want that data.
Yeah. So oh, sorry. Go ahead. Keep going.
You want to be able to net that data accordingly to how it's shaped.
Yeah. So we can kind of classify different data into these different shapes, right? And say, we know what this looks like. This is an exponential distribution. This is a Poisson distribution. There's another thing to this as well, and that's that these statistical distributions can be represented mathematically. Which doesn't sound like really that impressive when you hear it. It's like, oh, we can use math to represent these. But what's really nice about that is that we can make an analytical model. An analytical meaning that we can write an equation and say, hey, this is what this is theoretically supposed to look like. And then say, how does our data look like? Because our data don't always look like these distributions, like directly. So it's nice to say, well, how close is this distribution to it? Another thing we can note, really useful. Yeah, go ahead.
What kind of equation would you use to map the distribution?
Yeah, so it's not so much, you can use a mathematical equation to describe a distribution. So for example, an exponential distribution, we can say, well, there's some number times e to the power of some other number, essentially.
Oh, so it just represents the exponentialness of the distribution. I got it. Yeah.
Yeah. So we can basically say, okay, these are different attributes. And what's really cool about it too is that, oh, I lost my train of thought. What is cool about statistical distributions? Sorry, I'm losing my train of thought. Yeah, go ahead, Jessica.
Can you then make predictions with the equations?
Perfect. That's exactly what I was going towards. Yes. So if we know what the statistical distribution looks like, you know, like say, hey, this is a Poisson distribution. We can make predictions. And what's really cool about this as a data scientist, like, okay, we can use the data and say, oh, squint our eyes a little bit and say, does that look like a Poisson distribution, exponential? We can also use real things to test to say, hey, is this distribution actually what we expected? And what's even cooler, I think, is that we can actually say, hey, based on the quality, like where this data is coming from, right? We can say, what kind of distribution do we expect? And that's what we're seeing, for example, with COVID-19, is that we know virus infections follow an exponential distribution. And so we can make predictions, say, well, we know what exponential distributions look like, right? And we can start saying, well, what are those values supposed to be? Or what do we think those values could be? And we can, for example, you guys heard like flatten the curve, right? Like, it's kind of going around and stuff like this. One of the things that we can affect is basically saying how many people do we infect, you know, per, you know, infected person. So if you have a larger value, that basically every time, you know, someone's infected, we expect 3 people to be infected. That's a very infectious disease. But if we can reduce that, flatten the curve by social distancing and other measures, we can say, okay, like this exponential is not going to grow as much. And what's cool is that we can say directly, because of like how many people get infected from me being infected, we can say, oh, that's a value that we can put back into our exponential and predict then what we expect. And that's where, for example, you'll see a lot of like comparisons with different countries and stuff like that. I haven't seen too much with states in the United States, probably because not all the information is really well organized right now. But you'll see this a lot with countries and saying like, you know, how are they growing? And saying, you know, well, why are they growing this way? It's like, well, it could be because of the different measures they took in place to reduce, you know, this infection rate.
They actually were talking about it on CNN today, which the differences between the states and how obviously New York is like just underground right now, but a few other states are now ramping up in the same way.
Yeah, and it's really interesting, I find, is that me living in California, I'm seeing the rate of infection of like what that looks like. I've been kind of following the data and kind of like messing around with it. What's interesting is that you can see that compared to the whole US, and the US seems to be going up a lot faster than California, at least as of right now. And part of that reason, at least when you compare it to like initial infection rates, and part of that reason is probably because different states have different ways that they're doing this right now. So some states have put more stricter measures already in place. Some are just starting to do it now. Some haven't gotten to the point of doing that. So we'll probably see more ramp up in those areas. It definitely is a really interesting, I mean, strangely enough, like, I mean, all of this stuff applies to life because we're data scientists, but like you can definitely see some of this information actually like, oh, we can use this to actually see what's going on with something as relevant as a pandemic. So yeah. Cool. So that's kind of like, it's funny is that usually I kind of show statistical distributions and people are like, oh, like, but what do we need this for? Like what it, like, you know, not know what it needs for, but you can hear that like kind of tone of being like, but like, what exactly is this? Like, why do we need these things? And like, oh, whoa, we have a great example, you know, right now in the world. I don't know if great, I hope I'm not being too morbid or anything, but something kind of like look and compare. So one thing I want to talk about was like statistical distributions. I mentioned about statistical distributions like with normal curve, that's like my big focus and everything like that. I did want to mention a couple of things, and I'm looking at the time right now. I'll go through it pretty quickly. I'm not going to have you guys like, I'm just going to quickly show you the different distributions and talk about them like when these kind of occur. There are some also numbers associated with like the mean and the standard deviation that we expect from these things. Honestly, I won't even like, unless you're like a hardcore person who's looking at, you know, different distributions all the time, I wouldn't like memorize them. These are things that you can always look up or honestly have different functions that can simulate these or pull out this information. So first thing I'm just going to show you is distributions, which I think we didn't show this part from last time. Oops, I'm going to get rid of this guy since I don't need you, table of contents. We'll just have them hang out over there. All right, so this is actually more from like the curriculum. If you look at section I think that's what it was. So we talked about different statistical distributions. Basically, it describes and summarizes the probability of events in systems that, within a system or a group. So for example, rolling a die, for example, what's the distribution of rolling a die? Well, we get 1, 2, 3, 4, 5, 6 evenly. But if you roll two dice, right, two dice, and sum them together, like you have a different distribution than if just having one die, right? So that's kind of like why we use these different distributions. Classic is normal distribution, bell curve, Gaussian. You'll hear people talk about call it different things. Basically, I say common in the real world. It is like literally like almost like magical of how much this can actually come out. Like this is actually, I don't know if you guys ever seen this little thing where you drop the balls and like they bounce off, randomly off the edge and they end up actually falling downward. They actually follow a normal distribution. Pretty cool. And basically it's just about the randomness, where essentially what we're seeing is that most balls fall in the middle right there versus on the very edge. And the reason why this happens, at least in this situation, is that the ball, when it hits a peg, can either go left or right. Right? It's got about 50-50 chance of going left or right. And then it falls to the next peg and goes left or right. Well, if you think about that, it's kind of like a coin toss every single time. So the ones that land on the far left is like having like someone flipping heads, right? It's like left, 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 left. Where most of the time, most things are going to go equal heads, equal tails, just like left and right. So kind of cool that we see this stuff. I'll just kind of breeze through this. Useful equations. We've seen the equation for the Gaussian, right? That usually we talk about px being like the probability density, right? So note that again, like this x, that's probably not the best description, but the probability of x happening, we can actually just put x in here. I know it's really small, it's a little small in this, but all we need to know is like mu and sigma. And if we know those two parts, we can then say, all right, what's the probability of x happening? Usually we talk about range too. Is that like within this range? So cool. All right, so normal distribution, we'll see them more and more again, but I won't hold on that. So the other part is binomial distribution. So this is also a very common one. This is given the curriculum as well. It's basically the probability of getting the number of successes in a given number of trials. So you can kind of think about this like if you're flipping a coin, is like how many, if you say heads is a, what's it called? Like your success, right? So if I flip a coin and heads is my success, the binomial distribution says, all right, what if I flip my coin 10 times? How many heads would I expect to find, So sometimes see people flip a coin 10 times, they'll get 5 heads. Some people will get 6 heads. Some people will get 2 heads. Some people will get like, almost 10 heads, like 9, right? And so the idea there is the probability of that actually happening is going to get smaller and smaller on like the edge cases. So just the number of successes. And note that doesn't have to be actually, what's it called, a coin flip. It could actually be like an unfair coin. The point is like, what's the probability of success? That number could be whatever you want. And that's where basically we can get actually this mean is that, for example, ends come here, sorry. But basically the number of successes is basically the probability of those successes, right, times the number of times you do it. So if the probability of flipping heads is 1/2, right, and we have n trials, 10 trials, 10 times 1/2 is 5, right? So just like n times the probability of that success. So pretty straightforward. Standard deviation, we can kind of see something similar in here. Again, that square root, good old square root for standard deviation. But anyway, you can kind of pull this up. And then I just pull up point probability. Don't worry about this too much. You can find all this stuff on Wikipedia because Wikipedia is amazing. Cool. All right, cool. So that's, I think, the main ones that are really talked about in the curriculum. I can't even remember if there might be one other one that they mention. Honestly, it's been a while since I've actually like really gone through that curriculum and making sure like I got all those parts. But most of the things actually that we're going to talk about in this part are actually moved into the appendix, but I still think they're kind of important just to know about what they are. So for example, we talk about uniform distribution, the negative binomial distribution, geometric, Poisson, not Poisson, Poisson, and exponential distribution. Those parts are actually found in the appendix. So I think at least one of those might actually be in the curriculum, like in the main curriculum. But I have this little notebook here, and I'm just going to go through them really quickly because I don't think we should spend too much time on it since we got other things to talk about too, right? So